Okay, dear participants, good morning and good evening. Welcome to the fifth workshop live broadcast events of the 2023 Winter Polkadot Hackathon. And I'm your host, Tracy. Polkadot Hackathon is an entrepreneurial competition for Polkadot ecosystem developers, officially organized by Parity and OneBlock. It recruits Web3 technology enthusiasts from around the world to participate, promoting developers to create more innovative products for Polkadot and substrate ecosystems, and lead the team to invest in Polkadot ecological development and construction is underway. OneBlock will also help developers create teams, provide technical guides, and introduce investment and other support before and after the hackathon. And here, we also remind each participating team that after creating your GitHub repo, you need to submit the complete project information following the competition specifications. So there is where the official judges review your projects. So if you have any question, you can consult the mentors or staffs in the hackathon participating group. In addition, the total bonus, a pool of the three major tracks of the hackathon is $300,000, and other than that, you can also plus the bounty bonus that it can be stacked. So here I wish all projects team good luck. So today you can see our workshop info. We have two speakers, and I would like to remind everyone that the team that participates in the English workshop and check-in and then successfully enter the finals and participates in the offline demo day can share the travel grants bonus pool of 6,382 dots. So everyone remembers to drop the info, like your info is basically is your name plus your team name. Yeah, if you don't have team name, you can just drop like TBD, or if you're a personal like participant, you just drop your name plus individual. So next come to the session. We're very honored to invite Parity Core XCM developers and Parity engineer to share contents with you. So the contents covers various fields and tracks that everyone is interested in. And we have Francisco, and we have Subi Dong, and the Parity engineer will share the topics with everyone. If you have any questions during this period, you can record them first, or just write it down, or you can just post it in the chat box. If I will check the YouTube to help you to ask them. Yeah, if you join the Zoom call, you can ask directly after each session. So let's just start our first session immediately. Francisco, the Parity Core XCM developer, will share the topic with you, how to use XCM. Yeah, Francisco, you can share your screen.
I'm going to share my screen now. Tell me if it's working properly. Maybe not.
Well, I can see the screen now.
Good, then. Yes, I assume it works. I don't see the chat or anything, but okay, there we go. So yeah, there will be a time for questions later. So then I probably ask to see the questions in the chat. So welcome everyone. I'll be presenting how to use XCM, a practical guide on cross-consensus messaging. And I'll be showing you the fundamentals, some code snippets, and links to dive further. If you want to use XCM for a project, how you can do it. Great, so these are my handles. My name is Francisco Aguirre. I'm an XCM core developer at Parity Technologies. My matrix is at @syscode:parity.io in case That's the thing you use. And then my GitHub is at Francisco Aguirre if you want to know what I'm up to. So what is XCM? For those of you who are not aware, XCM is a language we use to communicate between consensus systems. That's what it stands for. It's cross-consensus messaging. And when I say consensus systems, I mean messaging, but it also means other systems that can reach consensus, such as smart contracts, for example, or anything really that can satisfy some interface. Here in this graphic, I'm showing like an XCM script or letter, which we call an XCM program, which is just a sequence of instructions, as we'll see later. And then there's something that's the transfer protocol that it can be swappable, and there are different protocols we could use. That is the thing that actually grabs our XCM programs and sends them somewhere else. So although XCM has messaging in the name, it's not a protocol for sending messages from one place to the other. It's just extensions that we typically want to do on consensus systems. So that would be things like transferring assets, things like getting NFTs or identity, voting, all those things, all those types of things that we would want to do on consensus systems. So if you've ever heard before of XCMP, that's a confusing name because that's one of the transfer protocols that we can use in the Polkadot ecosystem. But it has nothing to do with XCM. Like, it lives in a different XCM without needing to worry at all about how a message or whether a message is sent to another system. We could execute an XCM program locally as well. There's no need for a transfer protocol either. Okay, with that out of the way, let's talk about the XCM fundamentals. So there are three main concepts in XCM, which are basically what are instructions, which is the things our program is made of. Our program is just a huge or small list of instructions that we want the interpreter of our message to do, which that interpreter might be just one chain where we execute the program, or it might be that we're developing a palette with Frame, for example, or developing our own blockchain and we want to send some instructions to another chain. Then also, like, these instructions are things we want the other chain to do. Then these instructions need to reference things in the consensus system that it's being interpreted in. The things we usually care about are locations and assets. So locations are a way to represent accounts, which is something we really care about. But they're more general, so they let us represent accounts, things like governance bodies. I don't know, it could be multisigs, it could be many other things. So it's one of the things we care about and that instructions will try to reference, and they will use these locations we'll talk about later. And then we have assets, which they could be fungible, non-fungible, and we use the instructions to specify what we want to do with them, whether we want to withdraw some assets, deposit them somewhere, exchange them, and so on. So instructions look like this. These are three instructions taken from the XCM format, which is a specification that specifies both what a location means, what an asset means, how they are specified, and which instructions there are, which there are quite a few. So in here, we're only showing three very specific, very simple instructions that you probably see around a lot once you start developing some things with XCM. This is a very simple program, and it's very declarative. It says we draw an asset by some execution, so by some execution time, pay some fees, some gas or whatever, and then deposit the asset somewhere. Here we're not seeing like which asset, where, and so on. But that's what the basic of an XCM program looks like. And in the future, this program only has 3 instructions, but you can add multiple instructions, and you can have some error handling in there, some reporting back to the original system, and you can call, for example, frame extrinsics or like specific functions in the other chain. But let's start with this for now. And let's talk about what these things reference. So how are locations and how are assets represented? So locations are XCM's vocabulary for talking about where something is. And here we have a diagram of different locations on a possible relay chain, parachain ecosystem, which could be Polkadot, Kusama, or the testnets, Westend and Rococo. Locations are hierarchical because some locations consensus depend on another location's consensus. This is mostly apparent in, or let's say some locations' state depends on another location's state. So this becomes really apparent with parachains and relay chains. A relay chain is the parent of a parachain, because if something changes on the parachain, it has to change on the relay chain. And then we can extend this and say that a pallet in a particular frame runtime is a child location of a parachain, or an account is a child location of a parachain. And there we see accounts. But we have, or a body could be a child, and like a group of people, a multisig. So we have this relationship, and we can reference them via locations, and we usually do this in a relative manner. So when we interpret an XCM program, we interpret the locations in there relative to our current location. So let's say we have there like a parachain 1000 and 2006. Let's say we execute a message or a program. I will use those two interchangeably on the parachain 1000. Then we would interpret the location based on where we are. So we would go like one up and then one parachain down to get to parachain 2006. And we'll see how this looks in code, in Rust code, later. Then assets. How do we represent assets? We easily identify them via the location they come from. So for example, here our diagram changed from an abstract network to a concrete network, Polkadot. And here dot is the asset whose location is the Polkadot relay chain. So if on our program or in our message, we want to reference dot, then we would reference the asset that lives on the Polkadot relay chain. That's the Polkadot relay chain's native asset, which is dot. And then, for example, if we want to reference ASTR or the A star token, we will reference the location for the A star parachain. And we can, with this, it might seem more limited to like only specifying native tokens of a chain. But since locations are so general, for example, in the asset hub, we have the assets palette, which has a lot of generic indices for assets, and we use those for assets. So for example, on the asset hub, the foreign assets palette and a particular index, 1984, we have a USDT asset. And so also there we can see the account became more concrete, but the account doesn't have any native asset. For example, a smart contract might have a native asset, and so on. And we just use the locations to reference those. Okay, so how do we interpret these messages. We've seen that they're quite declarative. So we declare what we want to do, and now we have a language, have a vocabulary to speak about assets and accounts and so on. But how do we actually transform that into actions that can be taken? So every system, every consensus system or chain or smart contract that can execute XCM programs has to have an implementation of the XCM virtual machine, which is like the EVM, the Ethereum virtual machine, but it's not Turing complete. It's quite limited in what it can do. And it's basically dealing with assets and the locations, and then it can call extrinsics on the same or any type of functionality on the chain itself. And this XCM virtual machine has a specification, anyone can implement it, and there's a very configurable implementation that is meant to be easy to configure for your own use case, called the XCM executor. And here we see that all of these chains would have their own XCM executor configured to their needs so that they can execute XCM programs. And so if you send from one to another, it will be executed there and it will be interpreted as the system wants it to be interpreted. This means like maybe some systems don't have assets, so maybe they won't interpret instructions that deal with assets. Some systems might recognize some assets and might not recognize some other assets. So that's why it needs to be configured to each system to know what that system is capable of doing. Even if you express your intention correctly, it might be that nothing can be done with that instruction. So that's why these configurations come into play. Okay, so this is Rust code for how to actually write a message. And this is, there's a newer syntax, but this is what you will see in the documentation for now, which I'll link to afterwards. And in this one, we can see just a let message or let program creating a variable that holds the XCM. And in the XCM, as you can see, it's just a simple vector of instructions. And the instructions in this case are just variants of an enum. So here we have the same instructions we saw: withdraw asset, buy execution, and deposit asset. But we specify which asset and to where. How do we specify this? Where on the first instruction, withdraw asset, we can see a tuple saying parent and then a certain amount to transfer. And the dot into is just to turn it to the corresponding data structure. But the thing is, parent would be, we interpret it as the local consensus system. So if we were a parachain, then parent would mean the relay chain. If we were to be a smart contract, for example, then it might be the parachain where we are on. But here, if this was executed, for example, on Asset Hub or on a parachain, then parent would mean dot, like the dot token, and the amount is just the amount. And then with by execution, we just specify which asset we will use to pay for fees, which is the same. And we don't care about how long how much weight it takes. The concept of weight is just how long it takes and how much resources it takes. And then we deposit the asset, we just specify we want to deposit everything that this program has spoken about on some account, which we call Bob, which will be an actual account with 32 bytes on the local chain or on the local system. Now, where does this asset come from? We don't specify where it comes from. We do specify where to put it, but not where it comes from. Messages always have an origin, which is who is actually executing the message or sending the message. And that's the origin that will be used. That's the location that will be used to withdraw assets from. So there are, if you execute it locally, there's a way to get your origin, and if you send it, there's also a way to get the origin. So let's look at how, because this is just a REST program, right? This doesn't have anything to do yet with Substrate or Frame. So if we take a look at the Substrate architecture, a node is basically composed of two parts, some client stuff, which is like database, networking, all those things, and then probably, or most likely, a frame-based runtime, which has a bunch of palettes, and it's basically the runtime logic, the business logic of our chain. Here we have a palette. You can use other ones, obviously, but the XCM palette is a very simple palette to interact with an XCM executor and an XCM sender, so that we can actually send messages. It's a middleman between Frame and XCM, and in this case, it's the one that makes sure that if we execute a message, it has the appropriate Frame origin, which could be an account, so it knows where to withdraw funds. XCM is pretty abstract, and it's meant to be able to be used anywhere. It can be used in frame-based runtimes, it can be used in Ethereum, it can be used in Cosmos. It's just a language with a bunch of instructions and very generic ways of referencing things that can be run anywhere. You just need to implement the virtual machine and know what every instruction means. So here the XCM palette is like Frame's interpretation of XCM. And it has two very useful extrinsics or dispatchables to use, which are execute and send. Here we have an example of executing a message in Rust. And this one just calls a palette called the Polkadot XCM, which is the XCM palette. And it calls the execute extrinsic with a runtime origin of Alice, so that we know who is signing this transaction, so we know who is withdrawing funds in the message itself. And then we have the message itself, which would be the last one, like withdraw by execution and deposit. And we have some weight, which here we just put huge numbers, which is like the max weight, which we expect this to run. And we would get back an error saying that it took too long if we specify less. It's sort of like just a sanity check, so we don't pay like huge amount of fees, because we are paying for the execution of our message. Here you see some versioned stuff. That's because XCM is versioned. Here it says you need to wrap your message into a version 3. Version 4 is soon going to come out. And yeah, they exist to make sure that we don't break the existing messages when we add new instructions or when we change locations or whatnot. Okay, so this one lets you execute your message locally or your program locally. And then this one called send, appropriately enough, lets you send a message. So here we also sign the transaction. This is a thing you can call in your own palettes, by the way. So you could make the user that signed for your transaction to also call this. And then you send it somewhere else. Here, it's a versioned location. The multi is going away, don't worry about it. And the location itself is a parent parachain 2, which again, if this was interpreted on one of the parachains, then parent means you go up in the hierarchy to the relay chain, and then parachain 2 means you go down to a parachain with an ID of 2, which is not a common ID, it's just a test ID. They will usually be in the thousands or in the 2000s. And then you just send the message. And this will be executed by the transfer protocol, which in Polkadot is XCMB. But that's irrelevant to the actual execution of XCM. And then let's talk about sovereign accounts. This is more of like, how does the cross-chain or cross-consensus vision work for Polkadot. Not necessarily only for Polkadot, but the idea is that we have one main account and we need a way to represent that account on other systems or other chains that we send messages to. Why? Because if we execute it locally, then I mentioned that the way we know from where to withdraw funds is that the one who signed the transaction. But if we are sending a message and we specify, hey, I want to withdraw some funds, where do I withdraw them from? Like, it's a different system. I'm not going to be able to withdraw from an account from another system. That problem is still not solved. Like, there's no way. So what we have is a way to convert the location. So when we send a message, the receiver knows the location it came from. So let's say we send a message from A star to Polkadot, or in this case, let's say from Asset Hub to Polkadot. They know that that message came from Alice's account on Asset Hub. So what we have is a way to transform that location into a local account, which represents that foreign location. And we call that Alice's sovereign account. So in that way, Alice's main account on Asset Hub would fund the sovereign account. So it would send some messages to, you can either teleport or reserve asset transfer some assets, which you can look into in the documentation, which I'll share a link after this. You can like initially give some funds to that foreign account. And then whenever you want to handle things with that account, you just send a message and you don't need to specify anything else. Your location will be transformed to your sovereign account on that other chain. And so in this way, we have a main account and many sovereign accounts with all the chains we interact with by sending messages. And let's talk about what's next. So after this quick introduction to XEM and how it can actually be used via the XEM palette, I invite you all to go to the XEM documentation to read more about it and to download the parachain template, which comes pre-filled with the palette, with the XEM palette, and with an XEMP transfer protocol. In the parachain template, you need to run a relay chain and then some parachains, but then you can execute messages locally or you can send them and you can test that out. I highly encourage you, if you're gonna look into using XEM to leverage any other existing functionality in the Polkadot ecosystem, to look at the transact instruction. The examples I showed today were very simple, but I didn't want to flood you with many details. But the transact instruction is how you would call a particular functionality on another chain, or on your chain if you execute it locally. So it's what you most likely would use if you want to like reuse particular functionality from another chain in your own products. Like if you make a palette, you could do that. And also remember, since you can execute XEMs locally, you could just build the message you want to execute. You could just build it off chain and then call palette XEM execute, like make a normal transaction and just execute it on some chain. And from there, you can do the same actions in many chains. So that's it for me. Good luck working on your projects. And yeah, if there are any questions, I don't know how, because I'm not seeing the chat, but you can let me know. And if not, you can contact me via Matrix or GitHub or whatever.
But there's two questions from the chat you can check.
Awesome.
From the Zoom.
From the Zoom, nice. Let me see. Let's see. Okay, so is the full location concatenated from the various elements? Yes. We used parent and then parachain2 as a tuple. That means we go first to the parent, then to parachain2. If we wanted to go to a palette, we could go to the palette and then to the index, and that's how it works. The data structure is not a tuple, it's just we have a conversion in Rust from tuples to this data structure, so it's easier to use. Let me know if that answers your question. And then if you want to communicate with more than one parachain, would you need several XCM executors, or would you have one that has different instructions for different parachains? Okay, so this is an important one. The executor lives on the receiver, let's say. If you're only interested in sending a message, then you yourself don't need to worry about the executor of the receiver. Like, let's say Palette XCM requires a receiver. So let's say every parachain on the Polkadot ecosystem has an executor, and they configure it however they need. Like they specify what each instruction means to them. That's very important. Like whether they use the balances palette for assets or the assets palette or something else, they need to configure it themselves. And then you just send the message to anyone or to everyone if it's generic enough. Like transact is kind of the only one that is not generic enough because it's very specific. But you could do withdraw, you could do transfer, you could do locking, you could do many other generic things. You can send that same message to everyone, and they will all interpret it according to them. And then there you go, you can communicate with any parachain in the ecosystem. The XCM philosophy, let's say, is to move the burden from the sender to the receiver. So instead of the sender having to know, okay, which parachain has which palette or which parachain has which feature, hey, I'm just gonna send them a message, like my intentions, and if they have it configured so that they actually don't have assets or they have a different palette, then it works. They configured it, I don't need to know about it. And that's how we can achieve cross consensus or cross chain communication. Let me know if that answered your question. I don't know if there's another chat somewhere, some other question.
No, yeah, there's another chat and from YouTube, but there's no more questions currently.
Good.
So yeah, if you have any questions, you just contact Francisco through the emails here.
Yeah, the email, I think I didn't share it. So it's just the same as my GitHub handle, which is Francisco Aguirre. And you need to add the, no, sorry, it's francisco@parity.io. Yeah. Yeah, I think I shared it. So yeah.
Okay. Yeah, thank you, Francisco. Yeah, have a good day.
Sure. Thank you. Yeah.
Thank you. Yeah. So guys, if you haven't dropped your name plus your team name, please do that so we can try to like you won't lose your chance to share the travel brands. Okay, I already seen Sue is here, so Sue, you can start to sharing.
Okay, let me, can you see my sharing?
Yes.
Okay, and when do I get to start?
Yeah, you can start now.
Okay. So, hi everyone, just welcome to the Polkadot Winter Hackathon. And I think in the past half a month, we have gathered some of the most exciting topics for the participating teams, and one of them is the account abstraction in Polkadot. So in this workshop, we will dive into what exactly account abstraction is and how Polkadot tech stack is geared to support it. So just join this workshop for some insightful discussion. So as you can see on this slide, today we are going to dig into what account abstraction really means from a technical standpoint. We will also take a closer look at how Polkadot's tech stack with Substrate and its core naturally support account abstraction. And to wrap it up, we will chat about the current status of account abstraction in Polkadot ecosystem. And if we have some extra time, I think we might even compare how Polkadot approaches account abstraction compared to the other ecosystems. So let's go. First, so the first thing first is for those who might not be familiar with the idea of account abstraction. Let's give it a very straightforward definition right here. Account abstraction is to make account an independent concept and separated from the strong dependencies on like signature algorithm, transaction fee detection, and transaction initiator, and even the blockchain network. I know this might sound general, so let's just get to some details about it. So the first one, the effects of the account abstraction are mainly reflected in the following 4 parts. And one is the signature abstraction. It allows that the different accounts, accounts maybe is miscontracts to use different signature algorithm. And the second is gas abstraction. It allows for fee payment using different models, such as some support third-party fee detection. And the third one is nonce abstraction. It allows for different replay protection mechanisms, not just linear nonce increment. For example, we can have different types of transaction, and they may have their own unique nonces. And the last one is network abstraction. So it means we can control accounts or contract accounts on the other chains through the cross-chain messaging. So these 4 parts, all these 4 aspects, we can see that the central technical concept of the account abstraction is decoupling. So we will dive into the decoupling further later. Yeah, if you want to gain a deeper understanding of what is signature abstraction, gas abstraction, nonce abstraction, and network abstraction, the best approach is to integrate the understanding of those concepts into the life cycle of a transaction. Firstly, at the very beginning of the transaction life cycle, at the very beginning, we need a private key to sign the draw transaction. It will generate a signature. Then we send both the transaction with the signature to the blockchain, effectively to the blockchain nodes. And these nodes will verify the signature and the transaction. Then they will compute the on-chain address that needs to be operated on. Following this, the next step is we pre-detect some fees from this account, from this maybe on-chain address or on-chain account, and execute the transaction logic. Finally, some actions are taken to refund. like any remaining transaction fee. And this is like a whole complete transaction life cycle. So in most of the blockchains, the signature algorithm was like typically fixed. We could not freely choose the signature algorithm, so we have decoupled the actions from the signing and submitting the transaction to the chains. This means we not only have the freedom to choose signature algorithm, but I can even eliminate the steps of verifying the signature algorithm. We can custom customize the binding relationship between transactions and accounts. And this decoupling is what we referred to earlier as signature abstraction. You can see here that if we decouple the private key, like the signing algorithm and the on-chain account, and this part is what we call the signature abstraction. Adding a little extra context here, like in the blockchain setups, an account address is typically derived through hashing its public key, along with some other like truncation or manipulation steps. Now, if we have like decoupled the algorithm between the public key and used to submit the transaction and the on-chain account, we can we open the door to some interesting possibilities. So we can take Swiss ZK login, for example. It allows the public key to submit transaction having no direct connection with the on-chain account. And this too is part of the signature abstraction. So next we will take a look at the nonce abstraction. We have already known that if a node, like when node check if a transaction is legit, it is like to making sure that there's no mix up with the order of the transaction. Each account has a number called nonce, and it usually goes up by 1 for each transaction. So if the nonce in a transaction does not match what is expected on chain, and this transaction can always be considered invalid. So the catch is, the limitation here is that the algorithm preventing nonce conflicts is fixed, and accounts can only have one unique nonce. If an account could have multiple nonces, and the chain could, that is to say that the chain can support different types of transactions. Additionally, if the nonce collision prevention algorithm is upgraded, new mechanism might emerge, decoupling the relationship between nonce and accounts as well as nonce and transaction is what we refer to as nonce abstraction. So let's moving on to the next part. Next part is gas abstraction. Usually, usually the on-chain account we derive from a transaction is the one we pre-deduct fees from. But here's the twist: many new layer 1 solutions now support sponsor transaction. This is basically decoupling the account that pays a transaction fee from the account that executes the logic. This is what we mean by gas abstraction. It's like breaking up the Euro link between the paying account and the one that carry out the action. Sometimes gas abstraction is obtained through decoupling the account or the public key that submit the transaction to our chain, and the one that we pre-deduct the gas fee from. Anyway, we could see those as we like decoupling the two accounts. Like one is for maybe for the one is really executing the auction logic, and the one is for paying the fee. So finally, imagine if like through the cross-chain interactions, transactions or messages on one chain could control the behavior of the account on another chain. This is what we mean by network abstraction. It is like having transactions or messages from one chain, like it can really influence what happens on a different chain. So we could see that really like what so like through like this slide, it's quite clear that we can see that by examining the decoupling of the different stages in the life cycle of a transaction, we can understand what these four perspectives that come into play. So naturally, we can like through the analysis, we can like get the pros of the account abstractions. Like first, of course, it will support multi-sig, and also we can like support hybrid. We can have hybrid permission control or keyless login, like we often talk about the social recovery, the batch transactions, or in Polkadot, the scheduled transaction, or in Tued, the sponsored transaction. And also what we always expected, the multi-token gas payment or the low-cost wallet migration, because like we don't need to carefully remember the private key. And yes, of course, the hybrid private key custody strategies, or introducing like if we have like handle the problem with remembering the private key carefully, or taking very care of the private key, we can imagine that we could introduce the Web2 traffic into Web3. And also there is also this account abstraction. It can like optimize for some specific field like cross-chain bridge or DeFi or something else. So like after talking about the general, what is account abstraction, the definition? And next, we will just dive into like the specifics of how account abstraction is manifested in Polkadot. And first and foremost, because some teams are interested in implementing account abstraction project on Polkadot, we will focus on discussing how Polkadot supports account abstraction at various stages in its technical stack. And then we can take a look at which modules or palettes the current runtime layer of the Polkadot or substrate. Our substrate has like already support account abstraction. Like like before, we want to talk about what the definition is. The account abstraction, we need to talk about the life cycle in the blockchains. So the same here. If we want to to understand how exactly the Polkadot gain its account abstraction, we need to first understand that what is transaction in Polkadot or in substrate. I think we should just start it with the transactions in Bitcoin. So let me see, like when we talk about the transaction in Bitcoin, a transaction in Bitcoin may only represent a balance transfer. And in Ethereum, because we have EVM, a transaction can signify not only balance transfer, but also EVM calls. Essentially, on Ethereum, anything beyond a balance transfer requires EVM computation. So now in Polkadot, we no longer distinguish between the balance transfers and the other types of the transactions. All computations in Polkadot are treated as the runtime layer calls, including the balance transfer. So we refer to transactions in Polkadot as the extrinsic. So the extrinsic in Polkadot, it really means transactions. So here we, yeah. And so here, like we consider the runtime and like the entire runtime as a sandbox. Any information comes into this sandbox from outside is referred to as an extrinsic. You can see that we can notice that the XP implies external. So an extrinsic must have a source, which is called an origin. If we like delve into the substrate node, we will see several implementations of the origin. So first, it's signed that it you can like tell from its name that it indicates that it's initiated by someone whose signature can be verified. And the next is none, and then root. And the root is suggesting that some advanced permission accounts. Following that is proportion at least 3 or 4, which implies that if 3 out of 4 people agree on a transaction or on an action, it can be successfully executed. Like it's similar to what we understand as the multi-sig account. And like you can see here, like the origin root or proportion at least 3 or 4 or any others. And it can, like all of this can be customized in Substrate. Like you can really write your own logic, like to define some new origin type in your own Substrate node. So through this, like we get some like extend customization of the Substrate node. And finally, let's take a look at the origin now, which is quite intriguing. It signifies that the extrinsic comes from nowhere, means is internally generated. Like typically information written by the validators, such as a timestamp or other data that considered internal, would take this branch. So let's take like in the previous slides, we have shown some concept about the extrinsic and origin. So now here is the real code in Substrate, and like we can see from the code, like it's a checked extrinsic. The checked extrinsic, like it's come from the unchecked extrinsic. Like if we have the unchecked extrinsic, it means that its signature has been verified, and through the signature verifying, we have derived the account that submit the transaction. So you can see that inside the check extrinsic, we have like 2 fields. One is signed, one is function. And the signed, you can see that it may refer to some account ID, some on-chain account. And then there is a function. There is a function with the check extrinsic. It's called apply. You can see that like you can see that the maybe who is passed into the function as a parameter. So yeah, like this apply method is what we like proceed to execute the specific on-chain logic with. Like it's clear that we have like we pass the account the account ID as a parameter to this method and execute it. And this represents the fundamental pattern of runtime execution logic. Exactly because the origin is passed as in parameters to the function. So we have the flexibility to write code that we can replace the origin according to our need. This is a crucial part of code abstraction in the processing of implementing account abstraction in Substrate. In this apply method, we can also clearly see that the execution logic is derived into three stages. And the first is the pre-dispatch, and then dispatch, and then the post-dispatch. These three methods are defined in a tree, so we can like entirely re-implement this three methods to like achieve the account abstraction we desire. So from here, like we can get the logic execution mode of the runtime. So we have a function and we use like this call or the dispatch method, and then we pass the origin into the function and then execute it. So that means if we replace the origin here, like it means like some extent, like you can customize. Like you can decouple or customize your origin that carry out the on-chain action and other actions like in the fee or something else. So I think before let's it's more like it's clear to see like we go just directly into the code, maybe a better choice. Let me shift the sharing screen. Okay. So we see the code that is, we can see that we have some like on track. We can see there's an object called onCheck extrinsic, and it has the signature and function. And then we run the check function to turn the onCheck extrinsic into a check extrinsic. And this process remaining like the main things to do is just to like verify the signature. And okay, we now get a check extrinsic. We can see that in the checked extrinsic, we have an signed. It means an account, and also we have the function that comes from the unchecked extrinsic. And then we can see that what we talked about, the apply function. And then you can clearly see that this, like, we have separate the whole process into the three steps. And the first step is to pre-dispatch, and then to dispatch. And the last one is to post-dispatch. It's quite clear, right? And then we go back to the slides. Let me see. We then go back to the slides, so we can see like from the code that first, the unchecked extrinsic transfer into the checked extrinsic through the check method. In this step, the logic just for verifying the signature, and at the same time, the on-chain account is derived from the public key. And so if you want to decouple the public key that submitted the transaction and the on-chain account, and you can do the customization here inside the check function. And then we have the check extrinsic, and then we use the apply function. And here we have the 3 stages: pre, dispatch, and post. So in the pre-dispatch, we typically perform operations related to deducting the transaction fees. And then in the dispatch function, the actual transaction logic is executed. And as mentioned earlier, the execution pattern in substrate runtime involves passing origin into the function. Therefore, we have the flexibility to replace origin with what our business need, essentially redirecting the origin. Yeah, and in this part, if we customize this part, and we could have something like sponsor transaction, and if we rewrite the dispatch function, and then maybe we can construct some batch transactions at this stage. And also you can see that we pass the origin as a parameters into a function, so we can also redirect or replace the sender with some other address. And the second is refund the fees. And we can see that there is an example just in the substrate code. Yeah, let's get back to the code. Yeah, you can see that this is a node runtime, and as a payment, let me check the transaction payment. Let me search for it. Transaction payment. Or it's, let me search. I have forgot what's the customize is. Okay, I will if we have chance, we will get to this part later. So we'll just skip this and just see the implementation of account abstraction in Polkadot relies on the palettes, and currently it now supported palettes includes the multi-sig palette, the proxy, and the batch. And inside the batch, we have a function that supports the derivation account. And also we have a palette called recovery, and it can to support social recovery functions. So you can see that this structure, the account abstraction structure in the APH, it has user operation, user operation pool, the bundler, entry point, and the paymaster, and the batch. And I can say that it can it can very easily be implemented in substrate, and it can be a native system mechanism. And okay, and this is ZK login. And the ZK login, I think it's a really good example to learn, it's a really good example to learn that how account abstraction happens in some chains. You can see that we in the ZK login, we mainly use some Web2 token, or we can see the JWT to log in, or to log in, or we use a JWT to relate it to that some on-chain account. And you can see here that if we see the ZK login and we see the we see something here. Yeah. You can see that in ZK login, we don't have some some common private key and public key. Instead, we use some ephemeral private key. That if you see, you can change your private key as often as possible if you want. So it decouples the private key or the public key and the on-chain account. So this is the signature abstraction. And then if we want to then we must use the on-chain account to pay the gas fee for us, because we will change the off-chain private key and public key often. So it decouple the one that pays the gas fee with the one that submit the transaction to the chain. So this is a gas abstraction here. And through this, you can see that with the signature abstraction and gas abstraction, and this is how ZK logged in to implement the account abstraction mechanism in Suite. So okay, finally, due to the time constraint, we might not have the time to delve into more examples of account abstraction here. However, we could just remember that no matter how a chain implements account abstraction, it will fit within the conceptual framework we discussed today. So I think that is all we talk about today. And thanks.
Thanks, Suvi. Yeah, if you have any questions, you can ask her. I haven't seen any questions till now. Yeah, so I guess that's it for today. Yeah, finally, I hope that all the participants have here will gain something from these shares. And thank you everyone for participating today. And I wish every president would achieve outstanding result in your project. Yeah. See you around.
And one thing.
Oh,
okay.
Yeah.
Okay, just one thing to add up, because
okay.
I have searched the chart asset transaction payment for a while, but we did not get this. So at last we can find this through we can find this, and you can see that we have to customize a struct or an object called card asset transaction payment, and then we to implement it with some functions. And through this, and this is how we can gain the effect that we can pay the transaction payment with the multiple tokens, not only with the native token. Okay, that is all my adds up.
Okay, thank you everybody. That's all for today, and yeah, let's see you next time. Bye bye.